Hello, hello. I'd like to talk a little bit about magma crystal or liquid crystal fractionation in the magmatic state. And I'd like to give a little historical perspective of that. I came across the works of Charles Darwin because when he was on the Beagle, he was actually starting as a geologist. He later got interested in species distribution and in animals, but actually initially he was interested in rocks. He was a geologist, in fact. And he later actually became quite a leading figure in the Geological Society of London. And he wrote a few pages in his book on volcanic islands on this topic. And he was literally 100 years ahead of many other researchers that later got this topic into the forefront of magmatic thinking a century later. So let me share my screen with you. And here is the screen. And let's see that I get this up. Yes, that should work. So here we have a little discussion of the history. So when Darwin actually, as a young man, went on the Beagle, he had a number of books with him. And this includes some French books, but also Scrope, Humboldt, some German books then, and Lyell and Daubigny. And he learned a lot about volcanic rocks from these books. At the beginning, in his notes, you can see he was not very confident in using some of them. And with time, with ongoing time on the Beagle and with his studies deepening as he traveled, he got more confident with that. So he learned, for example, that a vesicular rock with many feldspar crystals may be labeled a trachyte. It comes from Greek and it means a rough rock. And this is not quite the same as a feldspar poor, but olivine and pyroxene rich rock, which we term a basalt. And this started to kind of give him some tools to distinguish different rocks according to their mineralogy. He will later modify the use of the word trachyte to a feldspar and amphibole bearing rock. And intuitively, he started to design, therefore, compositional criteria that allow him to put rocks into classes, into types or categories. And this allows us to say, oh, that's an intermediate rock, an andesite or a trachyte, as opposed to a basaltic rock. So this was partly inspired by literature that he read on metal alloys and lead, silver alloys, for example, that were describing how crystals would form and how crystals may actually separate from certain areas. And he there also learned about bubbles and that bubbles might migrate. So light materials like bubble gas bubbles might migrate up, and dense materials like crystals may actually segregate downwards. And when he was then on various kind of stops like the Cape Verdes, he noted that in some cases we actually have dense crystals here that may settle at the bottom of lava flows, while bubbles may concentrate higher up on the lava flows. So he figured out that something like this that was described in some of these studies on metal alloys is actually going on. And here we have dense, in this case, mantle peridotites, olivine nodules, and up here we have bubbles. So here we have a segregation, and there's a little bit of a lower density of these clots, of these nodules in this part of the rock. And then we have a few of those smaller ones up here, but there's loads of bubbles. So you can come up with ideas, can develop hypotheses that the big ones would settle down and the lighter ones might be carried up with bubbles attaching to them, floating them up, and the bubbles would certainly rise towards the surface. So, and here he, of course, would see in the Cape Verdes all sorts of magmatic features. He would see little lava tunnels and things like that. And he would see that there's gas bubbles migrating up, pushing up the roof of lava flows. So he got a good feel that there is segregation, that there's a lot of action happening in lava flows when they travel. He also got very quickly convinced that basalt is a magmatic rock and not precipitated from ocean water, as some prior researchers believed. So when he then came to the Galapagos Islands, where he had a longer stay, he was really ready to test his ideas. So the Galapagos, an ocean island system with loads of volcanic rocks, allowed him to really go into detail there. So when on the island of Santiago in the Galapagos archipelago, which was one of his longest stays, his longest landfalls, there he had help. But we should state that very clearly. He had a servant, and there was the ship's surgeon, who was also scientifically minded, who helped him. So they had a little party of interested people and support people, including also a local guide. So they were guided around the island. They were not just exploring from scratch. They had support in terms of people carrying things, and they had people guiding them around. But here is Santiago, and he was traveling around as a member of the Beagle crew and in the archipelago, going backwards and forwards. But he stayed here October 7th to 17th, 1835. So he had 10 days. It's quite a good spell for doing some field work. So, and here's a little map or a little impression of Santiago Island in the lower right. And he basically made his way from the lower flanks of the island up to the top in the time he was there. And this allowed him to get some good impressions. And what he noted is that the flanks of the volcano had effectively a lot of basaltic rocks, which he figured was low in silica, while the highest point on the island, on the peak of the island, that would be up here, there was trachyte. There was a rock that was not as low in silica, was higher in silica. And here's actually some of Darwin's rocks, which are nowadays at the Geological Survey in, at the Geological Society in London. And the specimens are still available. So he had gabbro xenolith here in a basaltic rock. He had an olivine basalt, and here's a small specimen of this trachyte that he collected from high up on the island, and then some xenolith, which intrigued him as well, which gave him a sense that deep inside the volcano, there would be accumulation of crystals, while high up on the volcano, bubbles might migrate up. So he really started to think about the separation of crystals and magma and gases at that point. So he finds these plutonic inclusions, xenoliths, that carry the same minerals as the lavas, but much bigger and more concentrated. So he concludes crystals migrate. And he's thinking about a large magmatic system inside the island that allows gases to rise, magma and liquid to rise, but crystals to effectively sink. And in a way, that is what we would later call fractional crystallization. So here he made these crucial observations, and the flanks of the volcano, they would then sample some of these undifferentiated materials, and the summit of the volcano would have the most differentiated material. That would be the trachyte here. So he effectively put his finger on crystal liquid separation, on magma differentiation via crystal fractionation. So he then concluded that alkali feldspar is less dense than magma, and so it could actually float in basaltic magma at least, and therefore it could migrate to the highest point of the island. But there could also be some bigger liquid system conditions, as I mentioned, in which, of course, the denser minerals would actually sink. And then he says that plagioclase, calcium feldspar, pyroxene, and olivine, they all have higher densities. They would sink, and they make these gabbro nodules, these gabbro plutonics that later become xenolith. This way, chemical separation would occur, and it would actually result in different compositions of the magma at different parts in this larger volcanic magma reservoir or system. So this is still believed today to be one of the key features of creating a mother-daughter or a parental lineage of magmas. And here the separation of crystals and magma in a liquid state is fundamental. And Darwin actually got his head around this in initial terms, in initial steps already in 1835. So this took another 100 years until people like Wager discovered the Skaergård intrusion, and other people in the US were studying the Palisades Sill, noted that crystals would need to sink in order to create crystal concentrations at the base of a sill, and then they noted that there is more differentiated magma higher up in the sill. And Wager, for example, at Skaergaard, realized that there are sequences of olivine cumulates grading into pyroxene, grading into feldspar cumulates and things like that. And then Norman Bowen came along and he did a lot of experiments, and he worked out that basalt initially that would cool, would crystallize, and it would crystallize olivine, and then the pyroxenes, and then plagioclase. And once we form these minerals and cooling continues, we get a sequence of new minerals forming. Plagioclase continues a little longer, but at some point amphibole or hornblende would form. Later we would get micas, K-spar, and quartz, and the silica would change accordingly in the residual liquid. And from 100 parts basalt, we would make about 5 to 10% of this high silica liquid at the end. And in very simple terms, this is something I drew up for my undergrad class. If we start with a basalt magma and we let this crystallize and we don't remove anything and don't add anything, well, we make crystals and we have a residual liquid. This might end up as coarser crystals in a finer grained groundmass or something like this. If we leave it on the ground, it will be platonic and there will be only effectively large crystals. But if we erupt it, then this might be the result. But if we start to remove crystals, then we can change the liquid, and that's important here. Here we have, for example, olivine crystals and pyroxene crystals, and if we segregate them out, we will have a liquid that is different from the starting composition. This residual liquid that might then be a basaltic andesite would have produced a cumulate of mainly olivine and some other minerals that would be a peridotite. And if this upper liquid here, the residual liquid, can move further, segregate further from, say, a magma reservoir, we might have more crystallization in that liquid, and then this basaltic andesite magma might then crystallize, produce a gabbro-cumulate and a new liquid, a new daughter liquid, which would then be, for example, an andesite liquid. So Bowen demonstrated this, and Wager and Brown saw this in the field in layered plutons like the Skaergaard, and later also in other ones like on Rum in Scotland, where I have done a little bit of work, certainly when I was an undergrad, and I'm still having an interest there. So here the concept is that crystals form and they segregate. We now know it's not quite so straightforward. The segregation is a bit more complicated, unfortunately, but here we go. This is the fundamental concept that you can all test at home. If you take a beaker with a salt solution, and this is a warm one, then a warm salt solution, and you let this cool and potentially even evaporate, then what will happen is that at some point there will be a saturation of salt in the liquid, and you'll start to have salt crystals, and they will form around the margins of your container, and if they fall down, they will concentrate on the base of your container, and therefore they make a cumulate. And this is a simple analogy to what we think is happening in magma reservoirs, where we have concentration of crystals at the base. So, and obviously there will be a change in composition of the residual liquid, of the residual magma, if we use this analogy. And here, depending on where you are in this kind of mixture between salt and water, you will have a different concentration of salt in the residual liquid. And this, if erupted in a magmatic situation, would give us intermediate to potentially very high silica liquids. So having said this, this allows us now to summarize this. This is going back to my undergrad supervisor, Colin Donaldson, where we have a parent solution or parent magma, and we isolate crystals, salt crystals. Then we get a daughter solution. From that, we can isolate yet more crystals, and we get another daughter solution. Magmas are not so simple. They are a multi-component system with more crystal types on the go. So if we have a parental magma, a basalt, we will isolate, for instance, olivine and plagioclase crystals to start with. We make a daughter magma of andesite liquid, then we might isolate then pyroxene, plagioclase, potentially hornblende, and the daughter magma might ultimately be a rhyolite. Now, in reality, this is not done in steps. It's a more gradual process, or you could separate it in many, many zillions of small steps. But Mr. Bowen, he realized this was back in the 1920s already. And Bowen was a pioneer here. He is a Canadian who worked in the US for much of his life, his work life, and he was working at the Geophysical Laboratory in Washington. And here you see him as a young graduate and as well as a somewhat more senior researcher here. And he did experiments with hot magma liquids, and he came up with this sequence, and he realized that there is a change in the composition of the liquids depending on the crystals that we are forming. A painstaking, meticulous type of work that he did, where he had to do many experiments at different stages, in the hot state, in the mediate state, in the evolved state, and at different pressures, for example, as well. And not just multiple temperatures, but different pressures. And then you get a system that he then summarizes in what we nowadays know as phase diagrams. But I don't want to go into phase diagrams too much. I'd rather want to give you some natural examples now to keep this rather simple today and rather qualitative. And here, I think one of the best examples we have is lava lakes on Hawaii. And here's one of these lava lakes on Hawaii. You can see that it's cooling. And there's also a bit of a crust here already, and the crust is pushed around. There's a bit of microplate tectonics going on. And here is a fissure eruption, and the lava from the fissure eruption is filling the lake. So here we have a bit of an analogy to a magma reservoir. So here, lava lake is then cooling, and here at the surface, we see these polygons that are forming when lava is cooling. And of course, the Americans have studied this, and the USGS has actually drilled into the lava lake once the crust was sufficiently solid. And what they found is that there is, of course, a temperature profile, and the crust is very thick at this point, so you can walk on it. But in the middle, there's still elevated temperatures. And here, the drilling gives us actually a sense for the different rocks in there. And this is what happened. This is now in Fahrenheit. So the rocks that had cooled a lot, they were coarsely crystalline, and the rocks that are in mediate temperature, they are less crystalline, and there's a bit of glass in there. And the rocks that hadn't really kind of cooled very much, they had a lot of glass and a few crystals. And it was interesting to see the glass in those portions that hadn't cooled very much. That was still mafic, that was still low in silica, while the little bit of glass, the brown batches here in the material that had cooled and crystallized to a large degree, there we actually had high silica glass droplets left in the interstices between the crystals, showing that indeed by fractionation of olivine, pyroxene, amphibole, and so on, we actually make a very felsic magma. And we can go from a basalt all the way to a rhyolite by this process. So it seems that Mr. Bowen was right, and in fact, Mr. Darwin, 100 years before Mr. Bowen, from the natural evidence we see there. And a few words about layered plutons. Now, it's quite a magnificent thing. There's these large plutons, like here, the Rum Pluton in North West Scotland, and there we have layers of rocks, and these layers, they are repetitive, and there's a cross-section through the layered Pluton, going back to Emeleus et al., and Emeleus in his memoir. And here we see these layers of peridotite, olivine-rich rock, grading into feldspar-rich troctolite rock. And this is a repetitive sequence. And here we see this in the distance. You see multiple layers here. And this is the mountain of Halliwell. And there we have different layers coming through. Unfortunately, there's a bit of a cloud. The weather isn't always the best there. So, but there's also another layer sticking out. And the olivine-rich rocks are weathering back. They are less weathering resistant. And the feldspar-rich rocks, they stick out, giving this profile, this layered profile. And if we look at this in detail, then we'll see that this is effectively a magmatic sediment. This is material that was deposited at the base of a reservoir. Here we see the geological map, and we see the margin of the igneous complex here. Here's the old magma reservoir, and here are these layers dipping towards the center of this plutonic situation. And here we see sedimentary structures like individual layers, and here's a block that had fallen down and it had impacted on this, a bit like a drop stone. And here we see also a bit of swirly patterns. So some of these sedimented crystals were mushy and they were moving and deforming, partly under their own weight, probably by moving towards the center, which in this case was a fault line, the long Loch fault here, along which most of the magma must have risen up. So, but here's the crucial bit of evidence. This is going back to Mr. Brown, and he looked at this in a lot of detail in the 1950s, Brown 56. And he noted that, of course, there's all these sedimentary features in the rocks, and he took one of those units. This is height in feet, so 300 feet, about 100 meters. And he then observed the amount of crystals. And in the lower part of this unit, he sees a lot of crystals, up to about 80% in volume. And it drops to actually much lower percentages, maybe about 20 or less in the upper part of one of these units. And then he looks at plagioclase, and plagioclase is low in the lower part. But as soon as the olivine goes down, the plagioclase goes up. And he concluded, in my view, quite rightly, that the olivine must have been sinking down while the plagioclase was crystallizing later, and therefore it was coming on top of the olivine. Therefore, there was crystal liquid separation in this magma reservoir in the upper part of it. So, and here's a few shots from Rum. And we note, however, and I've shown you a block that had fallen down, that maybe it wasn't quite so simple. It's very hard for individual crystals to sink down. So maybe these guys are moving more like blocks of solidified material. When you think of ideas like solidification fronts, that you get onion skin crystallization around a magma reservoir, and eventually these things might get very dense and slide down into the bottom as slurries, as mush, or even as solidified blocks. And here we have Henry Emeleus for scale. Here's Liz, one of my former students. And here we're standing close to the blocky areas on Rum. And here we have what we call the debris avalanche deposit inside a magma chamber. And here we have these larger blocks. They're quite randomly oriented. They are layered in themselves. So they must have slid down from the roof and the sidewalls of a magma reservoir. And indeed, Mr. Wager had concluded this, that almost 100 years after Darwin, Mr. Wager has come to this conclusion that crystals segregate, that they either come down from currents as individual crystals or slurries, but they could also actually have these collapses from the sidewall. They would be traveling a lot faster, and then they would deposit, and plagioclase might rise up here, olivine might sink, and therefore you get this layered mush at the bottom of a reservoir in a magmatic system. So let me wrap this up. Convection will then transport crystals downwards. And here's the thing, this was work that Lawrence Wager did in the 1940s, and his PhD student Brown did it in the 50s, and many people have researched this afterwards. But the real pioneer was actually Charles Darwin, who really got his head into this in 1835, and he wrote no more than about 7 pages in his book on volcanic islands, and he left it at that. For him, the topic was probably closed, and he got interested in migration of species and birds in the Galapagos, and that took his attention away from this problem. So he never returned to the topic after that, but we have his record, and a great research field has emanated from that, but only a century after he actually dealt with it. So Darwin's views on the inner workings of volcanoes, quite a magnificent read. I recommend it if you have a chance. Darwin, 1835. And I close here and say thank you very much. Thank you very much for your time. I hope this was of interest. And if you're interested in more quantitative studies, then there is loads of material out there. I can also recommend some papers, but this is a very qualitative concept and how we achieve different magma compositions from the process of crystal liquid fractionation or separation. Thanks a million, all the very best, and talk very soon, I hope.